Alright, so that's part 2. I wanted to make these videos short enough that you could watch one and then go do something and come back so that you don't hate me or my crappy voice. So, we've just barely talked about a null hypothesis and an alternative hypothesis. So I want to get into that just a teeny bit more and go one step further with what the null hypothesis means. So you're going to hear a lot of talk about random chance. And so we've got to take into account this idea that random chance is going to screw things up just every now and then. So if we go back to the dart thrower example, say we have the best dart thrower ever. So here's my dartboard, and this guy hits the bullseye every single time. If that guy, in a normal situation, sat there throwing darts, if he threw 100 darts, chances are good that a couple of those are just going to be off. Not because he doesn't know what he's doing, not because he's not really good at what he's doing, but random chance just throws things off every now and then. So in order to say that this person can hit the bullseye every time, yeah, that's true, but we're going to allow a certain amount of error. So let's say on throw number 25 he sneezes, and his dart gets thrown off. Is he still hitting the bullseye every time? Realistically, yeah. Random chance caused a miss every now and then, but we could pretty effectively say that this guy's going to hit the bullseye every time. Same idea applies to laboratory testing and statistics in general. We've got to recognize that random chance is going to cause change every now and then. So, in this case, if we were to say, hey, let's prove that this guy can get the bullseye every time. Let's say that a bullseye is worth 50. So 50, 50, 50, 50, 25, 50, 50. So if we look at these data here, we would say, okay, he's not hitting it every time, this 25. What we would want to then see is this 25 just a random occurrence? Or is it something that actually happened? You know, so I might come in here and with this same dart thrower guy, I might predict, hey, I think there's going to be a difference in your scores if I chop off one of your arms, your dart throwing arm. I know that's extreme, but I'm driving home a point here. So I would have a null hypothesis that says there is no difference in score, between what he was getting before I chopped his arm off and what he gets afterwards. My alternative hypothesis would then say there is a difference. So then what I would do is I would have him throw the darts, let's say 10 times, we'll pretend those are 10 values, and then I'd have him throw the darts 10 times after I chopped his arm off. So 15, 50, 50, 10, 50, 5, 25. So if I look at this, already I'm seeing that these data are different. So I got some 15s and some 10s and whatnot in there. Here I had mostly 50s with a 25. So now what I need to do is determine, hey, these differences that I'm seeing between these two sets of data, are they random? Is this just weirdness that I'm seeing that I would have seen if I hadn't chopped his arm off? Or is there now actually something significant that's changing these two data sets? That's what the purpose of statistics is. So I'm looking at differences either between two sets of numbers or over time or whatever it is I'm looking at. What I'm trying to say is, are the differences here statistically significant than the differences here? Taking into account that random chance is going to get in here and screw things up a certain percent of the time. So it's this amount of random chance that we're allowing that we refer to as the alpha level. So oftentimes you'll see in the clinical lab, we keep our alpha levels at 0.5, or 0.05, sorry, which is 5%, or 0.1, or 1%. So basically what we're saying is that we're going to allow 5% of differences to occur. We're going to attribute that to just random chance. So if this guy, before I whacked his arm off, was throwing 50s 95 times out of 100, I'm going to say he's hitting 50 every time. And that those 5, misses, that's just a random occurrence. Now when I look at this, it looks like I've got more than 5% of these guys going funky on me. So what this is going to do for me now is it's going to say, hey, I've got something happening here occurring more than 5% of the time. It's not likely to be just random chance. So that's kind of the idea, and it gets a little bit more complex than that, but I want to try to leave it simple. Remember, alpha level is the amount of allowable random differences that we're going to have. Or we're going to say, if the differences are happening 5% or less of the time at an alpha level of 0.5, we're going to consider them insignificant. However, if I've got something changing or I've got differences above that 5% of the time, we're going to consider that statistically significant. So my null hypothesis, getting back to this idea, basically is telling me if the differences that I see between two sets of data are occurring less than 5% of the time, then I'm going to consider there to be no statistically significant differences between these two sets of numbers. The alternative then says there is a difference if I'm seeing these differences between my values occurring more than just 5% of the time. Or in other words, I'm saying something's actually going on here. The differences here, they weren't just random chance, it's because I whacked the dude's arm off. And that was his throwing arm, and now I'm seeing some changes. I gotta give him compliments. If he's hitting 50s with his other arm, he's pretty good. Anyway, that's the point I want to make, is this whole idea of allowing a certain level of random chance. And it happens in the lab. You're going to have an analyzer that every 100 samples it runs through, it's going to get a bubble, it's going to burp, it's going to have a slide that doesn't load right, or it's going to have a dropper that malfunctions. We're going to have random chance that gets in there a certain amount of the time. So we've got to allow for that using an alpha level.